So welcome back for the second lecture of week 1. So in this lecture we'll talk about the basics of text processing and tokenization. So this is the main contents that we will be covering in this lecture, that what does it mean to process the text input that you would give to an AI model, NLP model. So what does it involve? Now what is the tokenizer? Typically we will mention about white space tokenizer, that is very common for English and other such languages. And then tokenization has a new new birth with LLMs, like you would have a very new way of doing tokenization. So this was the byte pair encoding, or BP in short. So this is also what we will cover in this lecture. So what does it involve in processing the text data? See, text is typically a very unstructured sort of data. I mean, you would have like whole document and article and so on. So you would have a lot of text data like that. Now, and you can think of it as a sequence of characters or ASCII characters or whatever, right? Unicodes. Now, when a language AI has to process this text for various applications, like it has to do some generation, like it wants to translate this text, it wants to summarize this text, or it wants to produce some embeddings, like for finding similarity, or it wants to do classification based on that, right? It has to first process this input text, right? So what is the first step in processing this text? First step is identification of what are the units in this text, right? So the input text needs to be processed first for any AI application, and the first step is finding out the units, and they are what are called tokens, right? So like this is your input text. Students opened their books, and I want to process this. So first of all, I have to convert into some tokens, like I have to convert into tokens. So in white space tokenizer, I will say, okay, students is 1 token, opened is 2nd token, there is 3rd, and books is 4th. And then I have to give them some IDs by which I can denote them, right? I can do, so for example, how would I give them an ID? I will say, okay, I would have some predefined vocabulary. So you would have to have some way of defining a vocabulary. So let's say my vocabulary has, say, 50,000 unique words, 50,000 unique words, and each word will be given an ID based on where it occurs in the vocabulary, right? So it may be based on lexicographical ordering or any other ordering that you will take, and you will say, okay, the strings occurs at 11th number, it has an ID 11. Opened occurs at 298 number, it has an ID, right? So they will have an ID, right? And then you will do processing based on this ID, like you will give a representation based on this ID, you will feed them to any neural model or anything based on this ID, right? So the first step is finding out these tokens. Once you have the tokens, then you can find your unique set of tokens, so give your vocabulary, you can give an ID to each and do further processing. Now, little bit of background about this. So let's take a sentence and let's find out how many tokens are actually there. So this is my sentence. They lay back on the San Francisco grass and looked at the stars, and there, I mean, just a snippet from a sentence. Now I can talk about the number of types, that are what are the unique number of words here. This will be an element of the vocabulary. Vocabulary only has unique words, so a word occurring multiple times will not be in vocabulary multiple times, okay, but it would be counted as multiple tokens. So tokens is an instance of that type in the running text. So if a word occurs multiple times, if a type occurs multiple times, it would be counted as multiple tokens. So now let's count how many tokens are there. So you will say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So there are 15 tokens in this sentence, right? Now how many types are there? For that you have to see, are there some repetitions? So you will find out the word and has repeated, right? So you have one type less. Anything else? So you have the repeat it. So you have -2, so 15 -2, so there are 13 types. So 13 types, so it will contribute to 13 words in the vocabulary, right? So if you take a large data set and find out the unique words, typically that will be a vocabulary, right? Unless you want to reduce a vocabulary if it is too large. So now, how does this vocabulary grow with the number of words in the corpus? So we have talked about this earlier, like Heaps Law, but so typically Heaps Law defines how it changes. So let's say n denotes the number of tokens you have in a corpus, and v denotes the vocabulary, that is the number of types, right? So how does the size of the vocabulary changes with the number of tokens? So Heaps Law says that this has some relation which k times n to the power beta, and beta is higher than 0.5, right? So vocabulary grows with more than the square root of the number of word tokens. So an example like switchboard phone conversation, they had 2.4 million tokens, so only 20,000 vocabulary. On the other hand, in Shakespeare corpus, you have 884,000 tokens and 31,000 vocabulary. You see, I mean, so Shakespeare has data is smaller than the switchboard conversation, but it uses much larger vocabulary, right? That's why he's also very famous. He's very large vocabulary. And then there are other corpus like Coca corpus and Google Ngrams. You see 13 plus million. This is vocabulary. So that means there are 13 million plus unique, I mean, that many types, right? They have unique words. So that means they're huge, right? If you really try to find out the vocabulary on everything available on the web, this will be huge. And why this will be 13 million? I mean, this may have everything including, say, numbers, right? Or all different type of dates and URLs, right? All these things will also come into, right? When you will do white space tokenization, all this will also be counted as your vocabulary. So you may do things like you will truncate this based on, I will only take the most frequent words, say, so words that have occurred at least 5 number of times, or I'll say, okay, I'll take only most frequent 50,000 words. So you can do some approximation like that, right? But that creates a problem, like what would you do with the remaining words, right? So we will talk briefly about this. So now, so when we talk about different, so in a corpus you will have the connection between the number of tokens and number of types. Now these words are coming from a corpus, right? So whenever we talk about a data set, a corpus, they come from a corpus, right? So words are coming from a corpus. This is produced by a specific writer. So typically text will have a specific writer, a specific time, in a specific variety of a specific language for a specific function, right? And to understand the language, you need to have a proper understanding of the intention of the writer, of the speaker. Then only you can understand that fully. But you may not have all this information at the time when you are really processing the text, right? And that's why you do approximations. But for an ideal processing, you need to have all this information in mind to make sure the language processing is sensitive to the person who is writing, to the time that for which the person is writing, for the purpose for which the person is writing, and so on, right? So how do you make it sensitive to a particular information, right? To that information for which it was meant, right? So yeah, and they would have various dimensions like the languages. There are like 7,000 plus languages in the world, so it can be any of those languages. It can be mix of languages, right? It can be variety, and we talked about various language families, like which family it is. There can be other things like it may have abbreviations. So specifically when Twitter came in, so they were, even with SMS, people used to do a lot of abbreviations. So like I don't, they would write I don't, right? And instead of 2, people will write 2, and so on. So there were various abbreviations that people may use. People may use code switching for the ease of writing, right? I mean, so suppose, so you are a Hindi speaker and you are chatting with someone, you may use words from English as well as Hindi for your conversation, right? So they would have, this would be called code switching. So you're switching from one code to another, from English to Hindi. But while you're writing everything in Roman. So like here, dost tha aur rahega, right? Don't worry, right? This is an example where you have a Hindi and followed by an English. So this is a code switching. So which actually means he was and will remain a friend, don't worry, right? But you are using Hindi in Roman script. And this creates a challenge. Suppose you want to convert it into the actual language, right? You want to actually write the Devanagari form. You have to know that this or is not English or. This can be English or Hindi or. Right? Dostha or rahega. So which one does it correspond to? So that is the task of code switching. It's also a sequence labeling problem, that given a sequence, find out which word corresponds to which language. And another example from Spanish and English here. Now, corpora may have genres, so there may be fiction genre, news genre, scientific articles, Wikipedia. There may be government documents, right? I mean, different kind of documents, and each document may have certain domain knowledge that also comes in, like a certain word, if you are using in scientific domain versus you are using in news, may have different interpretation. Right? And then who is the author, right? So what is the age of the author, gender, ethnicity, that also plays a lot of role in the corpus. Now, so text typically comes from different corpus, but when we are using the corpus, many times this information may not be available to us. But whenever we have it, if we can find a way in which we can use that, that will be always beneficial for the processing of language. Now how do we process? So given this brief background, how do we process this text? So we talked about this white space tokenization. You are given an input, and you can simply use white spaces and do the tokenization. Right? So like here, students open their books. I can tokenize using white space and say these are my 4 tokens. And I will give them an ID going forward once my vocabulary is fixed, and I have a unique ID for each word in my vocabulary. Now, white space tokenization may not be always like so easy. I mean, there would be issues even in English, like there are conjunctions, isn't. So you would say is, and you typically don't write it standalone, right? So now that's a dilemma whether I should convert it to not, or should I keep isn't as a single token. Similarly, prize winning, should I keep it a single token or call it 3 tokens, prize, hyphen and winning? Great movie, exclamation, will I call exclamation as another token, or what should I do, right? And typically you will see various tokenizers like Spacey and all, they would use a lot of different rules to handle these special cases, right? So they would already have handled these cases. Now, what if a new, so till now what we have talked about, so you would create your vocabulary that will have a fixed number of words. So vocabulary will be always fixed. So V is always fixed. Then only you can give this IDs to each word, right? And so what would happen? So once you fix your vocabulary from some data, and you are processing, and you come across a word that is not in your vocabulary, right? So how do you handle that? So what if a new or infrequent word appears? So infrequent I am saying because many times when you are creating a vocabulary, you may only take the frequent words. You may remove the infrequent words from your vocabulary. So what would you do with that? So these are called out of vocabulary tokens. So words that are seen very rarely during training. So training means from whichever data source I create my vocabulary or anything else like embeddings, or they have occurred very rarely, or they have never occurred at all. Now, the models that are using a closed vocabulary, they would be unable to produce word forms that are unseen in training data. They would not be able to make use of that. So what is typically done whenever you encounter an unseen word? So you use something called unknown token, UNK token tag. So historically what is done? So whenever you have a word that is not in your vocabulary, you replace with an unknown token. So this would have another ID typically in your list. So you will have an ID for unknown, and you will give that ID. So every word that is not there will get the same ID, right? So any token that was not part of the model's vocabulary will be replaced by this unknown. But so when you are generating, you should not generate unknown, because you cannot give a surface realization. You cannot generate a word replacement for unknown. Right? So, and yeah, I mean, there are problems for languages other than English that are morphologically rich, like languages like Sanskrit, where for the same word you may have multiple different morphological derivations. Like if in noun can have 24 different derivations, right? 8x3 table, and verb can have like 3x3 in each tense, and there are many tenses, and so on. So removing rare word will become very, very infeasible, because there are many words in your vocabulary that are very rare. So then how do you handle the situation that when there are many words that are rare, right? So how do you handle? Unknown is not a good solution, because first, every rare word will be treated exactly the same. Right? They may be very different in meaning, in the spelling, but they will be treated exactly same. They will be replaced by unknown token. So this is one problem. Second problem is, so token for every rare word. Second problem, you cannot generate a new word, right? Can't generate these words, right? So now how do you avoid this? Now, so here's an example like what will happen with unknown token. So you are given in a sentence, chapel is sometimes referred to as hen, gapple, ligvi, and so on. Now these words may have never occurred or are very rare in the data, so they are given the unknown token, right, while processing. And then that means you cannot do anything about these words, they are just unknown tokens, right? And same with here capel, so this will be written as an unknown token. So you lose a lot of information about the rare words or entities that may be crucial in certain applications. Now one option can be that you can decompose them into characters, right? The smallest possible unit of the characters, like example from Chinese, right? Now why I am also showing Chinese is because of the issue that unlike English, you don't use white spaces in Chinese. So when you write, so this will be a typical sentence in Chinese which has multiple words. So Yao Ming reaches the finals, right? Now the same surface form, you can treat it as 3 different words in Chinese, which means this, or as 5 words in Chinese, which means something else, I mean something related but different, or just 7 characters, right? So you see, so this is again a problem that in Chinese I cannot use white space tokenization. I would have to do some segmentation. I would have to learn what is the best segmentation among all of these, right? So how do you do segmentation? So that itself becomes a problem in languages like Chinese, and that is also common for say German compounds and other such languages. Now similar phenomena happens for Sanskrit, and it has a little bit more difficulty. What is that? So this is your input chunk in Sanskrit, Shveto Dhavati, right? Now these are what is being shown here are some plausible segmentation, may not be semantically meaningful, right? But what is the correct word in this particular context? Watch Shvetaha Dhavati, right? So it's a white horse, right, that is running. Now so you see, so when you are segmenting Shvetaha Dhavati, if you put together, you will not get Shveto Dhavati. Why? Because there is sandhi happening. So at the boundary of the 2 words, so you Shvetaha Dhavati, you convert into Shveto Dhavati by sandhi phenomena. So that means, like looking at the surface form of the actual thing that is spoken or written, I will not know the individual words. I have to use some algorithm to find out the individual words involved by using sandhi rules, right? And it may have other interpretation like Shwaitaha Dhavati, so the dog runs from here. It's a very another popular interpretation of the same sentence. So you may have multiple interpretations, and you have to see, given the context, which one is actually correct. So yeah, I mean, so 2 things that are conveyed from this slide, that segmentation or tokenization is not so easy for every language. So you may have to do segmentation separately. And second, you may go to character label also, but that may not be always good. It may be good for Chinese, but may not be good for English, because then you have to rediscover that there are words and so on, right? So because you will only know about characters, you will not know about words. You will have to rediscover that. But can we already give that information? So what is something that we can do that is in between the words and characters? So because characters will allow you to take care of any unknown words. Any unknown words you can break into characters, right? That's a good thing. But then you have to learn so much about words, right? So what is the midway? So that is what we will also see. So now, so while you process text, there are many other steps that you also do. For example, you may do lemmatization. So like you're saying sang, sung, and sings. They are all forms of sing. So can you take all of these words to the form sing? You do stemming. You strip the suffixes. That is another way of, I mean, simpler way of doing lemmatization without being grammatically correct in the final form that you generate. You just chop off some suffixes. Uh, you may have to do sentence segmentation if you need to know what are the sentences involved. So suppose your task is, I want to find the top 3 sentences in this document that are like a summary in 3 sentences. So I need to know the sentences, then only I can give the top 3 sentences. Right? So you will have to do sentence segmentation for this task. You may also do stop word removal because they do not convey much information, and you may do lower casing. So given the text, you may lowercase all, so that so when he is coming in as the first word versus he is coming in the middle of the sentence, you don't confuse it as 2 different tokens, because for computer, if you call he and he like that, there will be 2 different tokens. They will be given different IDs. But if you want to call them as same tokens, you have to lowercase, and you will lowercase, and you will say, okay, I'll call them as the same token. So you may do casing. So this was all done in the NLP, but with the pre-trained models, what is being seen? So we typically do not do any of these steps, but we do casing sometimes. So, and why is that? Because after you do all these steps, they are like mostly irreversible. So you cannot go back to the original data. So we cannot recover the raw text. Right? So that is why typically you don't do that. So with the deep learning, so the tokenization has got a new definition, as I mentioned, and this has a backing from scientific results that was found that if you use subwords, like don't go to words but go to a subword units, that gives you much better performance on machine translation if you do subword segmentation. And it also has to do with the technical requirements, that whenever you have to feed some text data into a machine learning model, a deep learning model, you need a fixed vocabulary. You need a fixed size vocabulary. So how do I achieve that? While I can take care of all the unknown tokens, right? By all I mean most of the tokens I can, right? So, and that's where the notion of token and tokenization has changed in the current NLP. So now when we say tokenization, it means segmenting a sentence into some units, right? They may not be typographical in nature, may not be linguistic always, but they are often smaller than the classical tokens, right? And they are called subwords. So in general, they are called subwords. Right? They may be words sometime, but they are in general subwords. And the previously, whatever used to be called tokens, that were typographic unit, they were like the sentence white space tokenizers. They are called pre-tokens, and whatever we used to call tokenization earlier is called now pre-tokenization. So you will take a sentence, you do compute pre-tokens, do pre-tokenization, right? And then you do tokenization by finding the subwords. Okay. So pre-tokenization typically is very similar to white space tokenizer, and pre-tokens are nothing but your normal tokens that we talk about in white space. But then we do something else with the deep learning architecture. Now, what are these? What are these subwords? Now, you can expect them to be meaningful units, like so they can be like morphemes. Morpheme are typically the smallest meaning bearing units in language. So if you see this word like unlikeliest, so you will have the morphemes like un, then likely, and est. Right? So there will be 3 morphemes in this word. And the branch that studies this is called morphology. Now, you create word forms by using a root form and creating multiple different suffix, right? You add multiple suffixes. So you can take a root form like if I give an example from Sanskrit, you take a root form like pat, and you get form like pathati, patataha, pathanti, right? Similarly, you can take example like play in English, you can get played, playing. So ideally, so they all give you new words in vocabulary. So if you want to reduce your vocabulary, what you could have done, for example, I'll say, okay, I'll take patha as my subword and taha also as my subword, right? So then patha will be common across. So I'll have one subword for patha and one for the suffix. And then I have a new word like bhavati. Again, this ti suffix here will be used for this bhavati here, right? So I would not need separate vocabulary token for each new word. I can break into the lemma and the suffix. So that is the idea. Similarly here play would be a separate unit and ed, ing can be separate units. That's what you want to do. Like so something like lower, you can say low and er can be the representation. But that is not always achievable, right? That is what is ideal but not always achievable. So byte pair encoding is one particular algorithm that tries to achieve the subwords. So what it does not use any linguistic insight, it just uses data. So you give it data, it will try to find out what are the ideal tokens given your vocabulary. So you give it a budget, this is my vocabulary, I want say 40,000 tokens. So it will find out what are the most promising 40,000 tokens given certain objective. Now how does it find out that? So it has two different phases. One is the token learner, that is what is the main part. So you take a corpus and find out the vocabulary, what are the set of tokens. And then you have a token segmenter that is at runtime when you give a new sentence, it will convert into the tokens and give it IDs based on its vocabulary. So it will convert into the tokens in the vocabulary. Okay. So let's talk about the token learner phase, that how do you take a corpus, raw data like any Wikipedia dump or anything, and learn what are the most promising, what is the most promising vocabulary from there. Okay. So this will be the process for token learner. So I'll take a raw trained corpus and I want to learn a vocabulary. So what I will do first, I'll pre-tokenize. I'll just do white space tokenization and append an end of word symbol to each word. Okay. Now I have to start from somewhere. See, in the worst case, every word can be treated as a sequence of characters that are there. So what I will do, I'll first take all the individual characters in my vocabulary. Next, I'll keep on finding out what are the most frequent adjacent tokens in the data, and I'll combine them into a new token. I'll create a new token. Okay, now I'll respect word boundaries while I do that. So if I find AB are the most frequent adjacent tokens in my whole data, I'll combine them into single word AB. And very importantly, wherever this A and B had occurred in my data, now I'll only treat them as a single token AB. I will not treat them as A and B separately. This will be a single token AB. I'll continue doing this until I have done some k merges, and k depends on my vocabulary size, right? And this all k new symbols in the initial characters is the final vocabulary. And what is this k? It's a nice research question, like what should be the ideal value of k, right? I'll show you some values of k from different models. So let's see this example. So on the left you have the corpus. So you have the word low occurring 5 times, lowest occurring 2 times, newer occurring 6 times, wider 3 times, new 2 times. So how do I start my vocabulary? I'll take all characters. I'll take L, O, W, E, S, T, right? All this will be L, O, W, E, S, T. So all these individual words, individual characters are in my vocabulary, and I have the end of word symbol also in my vocabulary. That's how I start. Now I have to find the new token in the vocabulary, right? So what is the new token? I'll find the adjacent tokens that are the highest, most frequent. So what I mean, like LO. LO occurs 7 times. But is there something more? So what about WE? WE occurs 8 times. Anything else? ER. ER occurs 9 times. It seems that is the maximum. I cannot find anything more than 9, right? So then I found 2 adjacent words that are the highest. So ER. Why I'm saying 9? 6 times newer, 3 times wider. So it comes 6 plus 3, 9 times. So what I will do, I'll create a new token in my vocabulary ER, and I'll replace this ER by a single token ER. So it will be like this. So they are now single tokens, and it's a new token in my vocabulary. And I keep on doing that until I achieve my desired vocabulary. So then next, what is the next thing? So LO and WE are, actually WE is gone. This is no more WE, right? So LO is still 7, NE is 8. Is there something 9? You see ER and end of word symbol. So ER, end of word symbol are occurring 9 times. So I can now use them and create a new token, right? So this will be my new token that is added, and this becomes, so I replace them by this. Next, what I can find LO 7 times, NE 8 times. I guess this will be NE. Let's see. So yep, NE. So I added NE here and merge them. What next? I may do any W, right, if nothing else. So I'll do any W, and you try on this on your own. So you'll find next after any W, you'll find LO. The 7 will come here. You'll find LOW. So you try on it, do this exercise, go back to the example and see if you can find these as the next tokens in your vocabulary. And you continue doing that until you achieve the desired vocabulary that you wanted. Okay. Now, this was a token learner phase. So after this token learner phase, you have your tokens in your vocabulary. There is also a token segmenter phase. That is, when you give a sentence, it has to convert into the actual subwords, right? So what will happen for that in token segmenter? It's very simple. So once you give a sentence, it will just use the merges that you have learned, right, and it will apply one by one. So first of all, you segment it into characters, and then you apply the same merge rule. So you will find E and R, wherever you find E and R together in that sentence, you convert into ER. If you find ER and end of word symbol, you convert into ER end of word. So like that, you apply the same merges again, and you obtain back the subword segmentation. And then you give the IDs and do whatever processing you want to do on top of that. So here's just some examples of different models. So you see like GPT-2, GPT-4, Star Coder 2, Llama 2, they all use BPE. There are other variations of BPE like word piece, sentence piece. I'll briefly talk about that. And you see the vocabulary size, they are very close, roughly like 30,000 to 50,000, right? Except GPT-2, which may use more than 100,000, but we don't know for sure, right? And if you want, you can play with different tokenizers on this particular app. So you can go to this and try different tokenizers on a given sentence and see the output. And you see also variation like cased and uncased variation of birds. So here in one of these, you will retain the original case, another you will do it in a lower case. Here's an example like in GPT 3.5 and GPT 4. If you give the sentence, have the bards who preceded me left any theme unsung, you see have the individual words, but bards is not being treated as single word. It is B and ards, right? So unsung is UNS, uns and UNG, and question mark is separate. So you find 13 tokens in this by using GPT 3.5 tokenizer. And this would be very popular. So like and this has many interesting implication, maybe not be good, like if you take the word super bizarre, right, super bizarre. So super bizarre, I mean, if you tokenize using bird, you will get superb and IGA double REH different subwords, right? And if you try to do sentiment analysis of this word, you will find it positive. Why? Because superb is positive, right? But this word overall should have a negative interpretation, but that it's difficult to get because of this particular subwords, right? So that has some implication. Another implication is on the cost, because all these closed source models, what happens when you generate token wise. So if in a language you have, for the same amount of data, you are using multiple more tokens, you have to pay more, right? So here's an example from this paper. So they did some analysis. So like if you're using latent script, what is the average number of tokens for the same data? So it's much smaller than say using say Bengali. So we are using more than double the tokens. Telugu, roughly 3 times the tokens, right? So that means if you are using the same sentence across say Telugu, you would have to pay triple the cost, right, for using. So that is one bad thing that also comes, and why you can guess, because it's all based on the frequency in the data. So if in your pre-training data, some languages are less frequent, there you will typically analyze them as characters or very small subwords. While if some language are very frequent, you will get, I mean, longer units there, right? So that's why if you take a sentence, a language that is more frequent in pre-training data will typically be analyzed into less number of tokens, and a less frequent language will be analyzed into more number of tokens, right? Okay, and there are other subword encoding schemes, like there is word piece, so which instead of merging by frequencies, tries to find out which merge increases the overall likelihood of the data. And then there is sentence piece, which does not require pre-tokenization. You can even, it is good for languages that are not wide space tokenized, like Sanskrit and Chinese. So you can take without pre-tokenization and start applying this sentence piece. So yeah, with that I think I'll end this lecture. So you can use the speech and language processing book chapter 2 to read more about this topic, and we will have some IPython notebooks to take you through the material that we covered in this lecture. Okay, thank you.